Right, let's try again. Well, thank you very much for coming, and welcome to people that are joining from far away lands. Streaming this on YouTube. That's exciting. So this is the Master's Defence for Jack McLachlan. We're going to have a presentation for about 40 minutes or so, and then open the floor to questions up until about 3 o'clock, and then we'll break for the close of the evening. Stay and ask questions at the end. So it's my pleasure to introduce Jack. Jack hails from a faraway land. He was in Scotland overlooking Loch Ness, and developed a really strong interest in natural history, crossing about on the high moors and hills in Scotland. And he did his undergraduate degree at the University of St Andrews in ecology and conservation, and he did an honours project on an area right beside the other famous landmark of Scotland, and that is St Andrews Golf Course, looking at restoration and rehabilitation of salt marshes that have been restored off that area. Jack came to Maine in the summer of 2014, and joined my lab when I was just getting started, and as I'm sure a number of you have joined new labs have found, it's a challenging thing to start learning the landscape with your advisor. It's certainly a lot of fun to be washing around the vernal pools and wetlands of Maine with a brand new student looking for places to do research. Jack's research really, I mean, one of the things I've been most impressed with Jack, and I think epitomizes the science, he has a really, really deep and broad interest in knowledge of natural history, and he couples that with a really strong understanding of conceptual ecology. And those two things are rare and becoming even more rare as ecologists move into model systems. So it's been a lot of fun exploring these landscapes and these things we get. Over the course of his environmental ecology, environmental science degree here at UMaine, he's applied a number of grants. He's been successful in getting about $5,000 of research funding, which is fantastic. He's had a paper published, an abstract published in Wetland Society and Practice. He's done an awful lot of institutional service. So he's the vice president of the graduate student government. He's been the graduate rep for the ecology and environmental science program. He's done a lot of outreach to K-12 and public through science days, through citizen science programs at Canadian National Park. And in his spare time, he's done a little bit of research. And Jack's research has really been pioneering the ecology, the benthic ecology of freshwater tidal marshes, a really understudied system. And he found the system himself after talking broadly about research ideas linked with hydrology and wetlands. Found the system, developed the research ideas, and the local context in order to be able to do the research as well, which is a really impressive thing to do at the start of the master's degree. And thankfully, when we went down to the freshwater tidal marshes of Swan Island, we realized they weren't a waist-deep mudfest, which made the logistics doing research a lot easier. So with that further ado, I'd like to pass it over to Jack to tell us about the forgotten cousin of freshwater community ecology.
Thank you everyone for coming. I realized that when I put my flyers out for this event, I did not put the second half title on those flyers. So I read the forgotten cousin of freshwater community ecology. Yeah, so I am not the forgotten cousin of freshwater wetlands that aren't right now. Hopefully the way that I get used to it. So I can imagine that everyone is not quite as intimate with tidal freshwaters as I am, but they really do exist. They may sound like they come in fictional terms, but they're actually very common. In fact, most estuaries on the eastern seaboard, and we think probably most estuaries in temperate systems around the world. So the tidal freshwater zone is the area between the limit of saline intrusion, so as far as the salt can penetrate an estuary, and it's the area between this line and the limit of where we still see tidal changes in water level. So this is this area here. And in these areas, you often find large expanses of freshwater wetlands that are very diverse and very productive. So if you're still incredulous as to how this can actually happen, these happen in estuaries where there's a lot of freshwater flow coming down into the river. Or alternatively, there might be some sort of aspect of hydrography that prevents the tide from coming out of the forest, and so you get what's known as a salt wedge estuary. So here, the incoming tide, salt water, is heavier than the fresh water, sorry, more dense than the fresh water, and so you get it starts to back up with very little mixing, and so as the water rises and falls, the tides that the coast receives are entirely within this freshwater block here. So there's no sailing at all. So, like I said, these are probably found in most estuaries, but at least in the northeast, in New England, they have been found in 13 estuaries from Passamaquoddy at the top here, down to the Merrimack River in Massachusetts, and they're all the way down to Florida. The largest of these areas, at least in the northeast, is Narragansett Bay, which is roughly 4,000 hectares of this tidal freshwater area, and most of it is vegetated by these very close wetlands here. And this is actually where my research took place a few summers ago. So tidal freshwaters tend to be in areas that are very heavily populated, and so they receive a lot of impacts, but they're also very important in the services they provide. Big things like supporting most of the anadromous fishes that we find in Maine, and also important for floodwater protection and for suppressing carbon. And understandably, then, the main focus that tidal freshwaters receive in terms of research has focused on the sort of like charismatic megafauna here that the fish and game species. And that's not surprising considering how important they are to tourism and things like hunting revenues and that sort of stuff. Additionally, because these are some of the most productive systems in the world, rivaling coral reefs or mangroves and things like this, there's a lot of interest in the ability of these wetlands to store carbon and sequester and to be able to ameliorate the effects of climate change. So a lot of focus is being on below that is what about invertebrates? Well, there have been a few studies, but really we really have no idea how these communities are structured. It's not surprising considering the very link between the charismatic megafauna that we care about for hunting and fishing, and the high-level product that we see in the plants and algae we find here. And so these are invertebrates are the main energy flow through the system here. And so that's the focus of my research. My research is to understand the factors that control these invertebrate communities and understanding this part to help us understand things a bit more about it. So we think about where tidal freshwaters are in the landscape. They're somewhere between non-tidal rivers and the lower parts of the estuaries. And because they kind of fall into this middle zone here, they've really been handled by limnologists who are doing the study inland waters. So as soon as there's any influence of the tides, then research interests tend to go off. And in the same respect, marine scientists are interested in saline waters, and then once you get into the water zone, there's no salt penetration, and so none of the species that marine scientists know around are found there. So this is why tidal freshwaters are forgotten as ecology here. And because they fall in this middle zone, there are multiple models that explain species diversity and the structure in the system. So the two realms can work independently of each other. So this is the estuarine model of species diversity, according to marine scientists. And they're going to generally observe is you see a decline in the diversity of species as fewer and fewer marine species are able to tolerate the swimming further up in the estuary. And in the same respect, because there is some salinity in the water, freshwater species aren't taken out into the estuary. But as we know, inside a freshwater part can actually its freshwater part, can be split into tidal and non-tidal. And so while salinity effects might explain this drop in diversity, it certainly doesn't explain why studies that have freshwaters are found to be less diverse, like a popular subset of the non-tidal portion of the freshwaters. And so The only difference I can see here is that the difference between tidal and non-tidal freshwaters is that tidal freshwaters have hydrology. So hydrology might be influencing this decline in this diversity procedure. And that might not be so surprising because in non-tidal freshwaters and inland waters, hydrology is the master variable that's been trying to control community structure and patterns of species diversity. So we imagine a gradient of habitat permanence moving from small, shallow muddy puddles that dry up frequently or unpredictably, moving through wetlands that burn pools, which may be dry seasonally, or small ponds that might dry every other year, up until permanent deep water lochs, which do dry up. It's never on the scale of the lifetimes of wetlands that live there is usually if we get at all. And so as we move up this gradient of permanence, the relative risk to the communities that live there of drying up declines as a function of permanence. And likewise, because these habitats are more frequently drying more frequently, they're also much less likely to support top predators and fish. So you can imagine these puddles which dry up every week or so, they're not going to have fish. And so the more permanent water bodies, the relative importance for predation in structural community increases. And so if you're a member of the invertebrate communities here, you're facing trade-offs here that govern how you complete your life cycle. So these habitats are dry very frequently. You have to have an expedited life history strategy in order to get from egg to adult in a limited time. Because you have a limited time, then you have to be actively foraging to collect enough energy to complete the life cycle. But the good thing about that is there are no predators, and so you won't be fishing any kind of energy to test possible defenses. At the other end of the gradient, these habitats don't dry up, so you don't have to worry about completing the life cycle quickly, so you can take longer. But because there are fish predators here, you have to be a bit more cautious around forage and how you collect energy. And some of that energy for future fitness has to be invested in some sort of defense, the defense against the chance to get included. So this model works very well for inland freshwaters, which are these discrete units of the landscape. But tidal freshwater is a little bit different. So there is still a gradient of hydrology here where during the tidal cycle, things that are low down in the like lower tidal heights tend to be remain inundated for longer, and then the high tide line is only really inundated relatively briefly right there. And so because there is this gradient of hydrology, there's also a gradient of predation here where fish can come and go with the tide. And so the trade-offs that structure communities non-tidal freshwaters are arranged differently to tidal freshwaters for these things. So the thing that I talked about in today's talk, and some of the questions that I had in the thesis, and I've broken this talk up into two main acts. In the first act, I'll assess the kind of previous studies that suggest that tidal freshwaters are less diverse than their non-tidal counterparts. So we'll see if that's actually the case. And because there is this gradient of environmental conditions in tidal freshwaters, I'll investigate whether communities in these areas are structured differently. So whether the trade-offs generate different community structures across the tidal. And the second part of my talk, we'll take a closer look at these areas, and if there is a difference in community composition, then we might expect a difference in the token structure or the trace find there. And then lastly, I'll get on my soapbox a little bit and talk about some ideas I've had for continuing with this part of my PhD, and argue the case that we should all be studying tidal freshwaters to help us understand some questions we have to take on. One. So we conducted a field study on Swan Island. And Swan Island is an island in the middle of the River. convection there. And so the Kennebec goes north to south here. These darker green areas here, these are uplands, and these sort of like grayish areas here. These are the intercredit mudflats, these are the areas. What we did is we laid out these transects to encompass 3 different tidal heights. And so these areas, so they look like this is the mudflat look like it's over here. And so all this area we put in water during high tide, and it really was going all the place to work, seeing sunrise, being nightfall, people's sturgeon, terrible. And these areas are relatively contiguous, very densely vegetated. So we see a lot of species here, and so it's a relatively homogeneous habitat. And so this is standing at the high water line here, and we extend the transect out to encompass these zones of tidal height. We did this so to be able to encapsulate a gradient of hydro period here. So at the height water line, these areas are irrigated for less than 3 hours of day during the day, and then the lower areas are irrigated for much longer. And because we were interested in the comparison between tidal and non-tidal wetlands, it also includes some permanent ponds that are very close by. And these are mostly deep water man-made ponds, definitely the maximum depth you can above the head height. And since they're quite deep, and they have these this little range of vegetation, this is for example. And we also included some wetlands that experience significant dry down. So these are sort of more temporary ponds. And these are things sort of more akin to pools that you get around here. Either they dry out completely or they experience significant dry downs. And these areas are much more shallow. The water depth never really getting from knee height or gets vegetated throughout the water areas. And so this color scheme here, where hydrocarbon sites are red, yellow, and blue, and the inlet sites are green and purple. The systems are at the top, so if you see any data points that are red, you know that that data came from the low tidal part of the transect, and likewise, purple data points will come from so we went out and we sampled community, converted the community of Vienna, and because we expected there would be large changes in large seasonal changes in vertebrate communities, we sampled 3 points, during the season to account for that. And because we expected there to be large differences between the environmental conditions between the low marsh and high marsh and the inland sites, we installed 10 data loggers. So these are temperature loggers that log the ambient temperature every half an hour, so we can get an idea of how variable the environmental conditions are. And what we found is quite striking is that this is temperatures on the y-axis here, and this is daily maximum and minimum temperatures for the month of July. And what we found is that at the high marsh, it's not uncommon for the habitats to get up to 45 degrees Celsius, which is exceptionally warm if you're invertebrate. The low marsh still got quite warm during the tide, but not quite as much, maybe 35. So, what's perhaps more striking is how much this can change during one tidal cycle. So this is the change from maximum temperature to minimum temperature. It can be as much as 32 degrees Celsius, which is a really large jump in temperature for any organism to experience. We found that was still large changes in the low marsh, but not quite as great as we saw further up the tidal. So here is we have a strong gradient of conditions, and it's worth noting after the data here that the temperature maximum minimum data for the headland sites were roughly the same as the low marsh, but because they were a little deeper and didn't experience the same water level changes, then you can't keep up with that slower. So the evaporation is slower. So when we collect your peanuts, we have to remove all the invertebrates from the samples, and then in August, we'll test it in the field, but sometimes it's very long time, so here we have eggplant, try this at night. But then you get it back to the lab, and it's all nice and clean, and then you can identify the invertebrates. In this case, we need to use and so what we found then, once we enumerate, is the number of invertebrates and the identified log. And these are our results. So on the y-axis here, we have the number of invertebrates per meter squared. This is on a log scale. And here are the habitat samples, and these are the samples. And so what we found is that between tidal sites supported fewer invertebrates per meter squared than either of the non-tidal habitat samples. This is and so if you notice here, while tidal sites supported fewer individuals per meter squared, the response is not consistent across the tidal. That'll be a thing that the rest of the talk. We'll get into that a little bit. And here we have comparing species between tidal and non-tidal sites. Because we did have those big differences in abundance between its sites, we decided to verify our diversity index here. So this is Margolef's index. Basically, the number of species divided by the log of all individuals we find. And what we found is that at any point in the tidal transect, tidal sites tend to be less diverse than their non-tidal counterparts. Again, this response was positive. So it does seem that tidal freshwater communities do appear to be less diverse than nearby non-tidal wetlands. And so the sort of finding the previous studies seem to be vindicated. But what we don't know yet is whether they're just the proper subset of the tested tidal sites, and non-tidal freshwaters. And to get at this question, we need to go back to our data set. And one of the ways that we can visualize similarities between communities is by using information. In this case, a multi-dimensional scaling plot. And essentially what this does is it takes the relative abundances of species and calculates the relative distance between them. In this case, we use the Curtis index. And when we plot the communities in this coordination space, which is constrained on two axes, what we can see is that if points are close together, then their community structure in terms of the richness and the abundances is more similar. So these points are more similar than these ones. And then what we can do is we can draw a line around all the community sampling particular habitat and say, well, this encompasses all the variation in community structure, composition for this habitat. And then if we join up the communities from a different habitat, what we see here is that the variation in community structure habitat A really is just a subset of the variation in habitat B. So this is what we would expect to see if tidal freshwaters were in fact, if communities were a subset of the structure of non-tidal freshwaters. And so this is all the variation encompassed by both habitat types and non-tidal, so primary and temporary. And what we found is that no, tidal communities and tidal sites were not a subset of the fauna that we find in non-tidal sites. Because and furthermore, in the same transect, there seems to be differentiation in the community structures between the low marsh and the marsh and the high marsh. So here we have very little overlap. It seems here that we have sort of community zonation that we need in rocky. And what's more interesting, I feel, is that even though these habitats are right next to each other on continuous transect, the variation in differentiation you see here is much greater than the differentiation between habitat types in inland, even though these were separate basins and were actually physically distinct from each other. And they could have aggregated. So the variation in tidal sites was greater than the variation between non-tidal sites. Again, this helps to dynamics. So if we look at all the taxa that we found on the landscape, and after we identified them, we found 107 taxa. And if we look at the where these communities overlap in terms of taxa found there, what's striking is that out of these 107 taxa, almost a quarter of them were only found in tidal sites. And these were things like a species called dragonfly, which is quite uncommon in the state, and also some rare beetles, firefly larvae here, and dark-winged beetles. They tend to use tidal sites, and they're not utilized. And it's an interesting site here, even though there was this contribution of tidal sites to their contributing unique taxa. There were about 30% of the taxa that were generalists. They were found in all habitats, regardless of whether it's a high marsh or 40 degrees Celsius in the day, or whether it was a very pond, which would change relatively little in its temperature or height. So these are things like all of these worms, mayflies, amphipods, and this beetle, Halopus. And it's interesting to note that Halopus is actually the beetle that can withstand the greatest level of desiccation of any beetle. It can lose 91% of its water weight and still function, which might be one of the things that persist across this great and defined conditions. So to summarize what we know so far, yes, it does appear that at any one point, tidal freshwaters do seem to have less species in them than nearby non-tidal freshwaters. That's probably the simplistic view of it because they really are contributing types of the landscape that aren't found in any of the other habitats. And so we are boosting the number of species to this portion. And furthermore, we saw greater variation between different zones in the tidal wetlands, even though they're right next to each other. Basically, they were contiguous. We saw greater differentiation and variation in communities than we did in these inland wetlands, which were hydrologically isolated from each other. And because we did see that such a striking pattern, we thought this warranted a closer look. So this is a random deck one. We saw strong differentiation in the communities here, and that's probably related to this very strong gradient of abiotic conditions and biological conditions that are related to hydrology. So you imagine if you're a member of a vertebrate community here, like this dragonfly, for half the day you have to contend with being dried out and under the heat of the sun. And then when the water does come back in during high tide, you're able to forage, but you're also going to be subjected to fish predation. And what we saw when we were out there sampling, we able to come in, so we the sample, as soon as the water was deep enough, and that's really a couple of inches, there was these vast schools of fish coming in and utilizing the areas of approach grass. So there really is a strong predation pulse here. And because we did see these differences in community structure, we would expect that we see differences in the traits that we often find there across the state. And so one of the easiest things, easiest traits to measure is body size. So we have all these invertebrates anyway, we're identifying them. And so all we really did was take a picture of them and then use the ability to acrobat the scale bar to measure these, measure the body lengths of these individuals. And then once you have this information, then you can use algebraic equations to convert body lengths and body masses into kilograms. And because we are identifying these things as genus or family, there's good information about what each was. So we know that these leeches and these dragonflies or predators, likewise these beetles and isopods, are to try to avoid and on getting organic material for their energy. I mean, all these snails and worms, farming leeches, their grades are super dependent on carbon production for their energy source. And so we look at these traits to get a better understanding of how these communities, how their food structures, how their food structure changes across the grain. And so what we found is here, this is after we converted body lengths into body masses. This is average invertebrate body size on a log scale in milligrams, and these are our results. And what we found is that the average body size of the invertebrates and the low marsh is significantly lower than the ones that we saw for other upper types of food. And although I don't have a direct cause and effect here, it's consistent with results that we've been finding from inland freshwaters where fish are very strongly sized like predators. And so if you're a larger body invertebrate, you're much more conspicuous for predators. You're going to represent greater payoff in terms of being predated upon. So there seems to be some sort of penalty for having a larger body size in the lower reaches of the size. And so once we have all of these individual body masses, we can sum them and get an idea of the total biomass of invertebrates at any point on the concept. And because we have that information as to what things do, we can partition these biomasses out into different components of the food web, find out whether there's a change in the importance of different energy pathways. So this is one figure, so I'll through. But essentially, the inner box here, this area represents the total biomass of that trophic level in milligrams per meter squared. And the outer box here is our standard error. So what we can see here is at the low marsh, it seems that the relative importance of the artillery is much greater than the importance of herbivore here. So we see fewer herbivores in the lower marsh. And we also see relatively lower biomass in the predators, the next trophic level up here. And that's perhaps unsurprising considering we saw a reduction in the average individual body size, and invertebrate predators tend to be larger bodies than the prey, just based on the contribution. And so what we see from the top titles of grading is the only just the relative importance of the energy pathways changes, but the total biomass in invertebrates altogether increases. So we see greater biomass of carnivores and herbivores and invertebrate predators than we saw further down on the carnivore side. And then as we look behind marsh here, there's less overall biomass than mid-marsh, but the relative partitioning of biomass along different trophic levels seems to be more even here. So we see relatively similar biomassing of lean energy pathway invertebrates, herbivores versus bright energy pathways, as we do with invertebrate predators. And so there are clear patterns here, and I don't have strong data to say of this, but I strongly suspect that the reduction, at least in predator biomass here, is probably related to prolonged and more intense fish predation that's limiting the biomass for the predators. And in the same respect, I think that probably it's the abiotically stressful environment, so there is very little time for diverse forage if you live in the high marsh, because they're only in really for a few hours a day. And so the air biomass might be limited by the abiotic environment. And then I think there might be some sort of fluid loss here where there's slightly less predation, slightly less abiotic stress. either for that. So what we see here in terms of different zones in tidal wetlands is that from Act 1 that we saw a strong differentiation in the communities in terms of their community structure and composition. And then we see differences in the distribution of invertebrate body sizes between zones that are very close to each other. We saw a reduction in the average body size and lower height that might be related to fish population. And we also saw differences in the relative importance of these resources and energy sources. And whether this is the predation of the environment, it's not yet clear. But what is clear is that even though these habitats are right next to each other, they seem to be structured very differently in terms of their composition of the structure. And so, I guess an obvious implication here is that small changes in hydrology could spell large changes in the total structure of these systems and how the communities code. And so, we all know the sea levels are rising, so we saw even minor changes in the hydrology, whether the sea level rise or also precipitation regimes, which is typically happening in the northeast in terms of the number of flashing floods that we see. We can see large changes in how these and I won't go on about that, but what I do think is very interesting, the fact that we do see these changes in large changes in communities, even though there's very small changes in hydrology. I think this is potentially very useful and an underutilized resource for community ecology. So I'm going to step up on that soapbox for a little while to talk and argue why I think we should all be using tidal fresh waters to answer some of the key questions in community ecology. So we remember our conceptual model is applied to inland freshwater. As we move along creating habitat permanence from puddles to nets, what we see is a relative change in the importance of desiccation risk, the biotic factor, and predation biological factor in their structural communities. And so this pattern has been shown across this gradient by previous authors. But in addition to the relative risks that remain dry up and whether it's called predators, there are a lot of other intrinsic properties of these systems that make them different from each other. So it goes without saying that small muddy puddle is nothing like a very long well. And so what we can see here is that there's massive differences in depth, basin size, productivity, complexity, and the likelihood that they're going to support our predators. So if we look at any point loans creating a habitat permanence, these factors are always linear. It's very difficult to get a polynomial arrangement of these things with manipulation. And it's also unlikely that you're going to get crop predators in these systems and this system will dry up unless you had some really hardcore manipulation. So there's also a lot of distance effects if you were to try and create a natural gradient. Things that are similar, more close to each other, and more likely to dry up. And in very few cases, it's very hard to get a collection of these study cyclones grading to test the questions that we want to get. And as we've seen in this talk, that we know that hydrology is the master variable in tidal systems. But in this case, our gradient is continuous. And it's a relatively homogeneous, contiguous habitat. And we still get a gradient of desiccation risk. In this case, it's on days rather than seasons or longer. And so we have a gradient of hydrology from the subtidal area that never dries at all because it's not getting exposed to the high water line, which is very frequently flooded. And because we have this, we do also have the same gradients of predation pressure, but because this is aquatic habitat, it definitely has water in some part of the day, arguably predation is never zero here. So the relative importance of predation is never actually zero, because pressure actually always is. And so you might be thinking, well, this is very similar to the graphs that we saw in the models that are applied to inland freshwaters. And you say, well, these things are not orthogonal either. These lower areas are less likely to dry up, and they're also more likely to have fish pressure there in the day. But the benefit of tidal systems is they're very amenable to manipulation. So building on what we found in this sort of preliminary observation-based study in terms of structure, these are some of the ideas I have moving forward as some ideas I think more probably applicable to other people's questions. So we can install these predator exclusion cages, so you can essentially remove the influence of predators in the system, and by doing that, you can make this flat line, and then you can really get at the relative strength and importance of desiccation risk in terms of structural communities, and how that influences the traits and competition communities in the system without the confounding intensification. And likewise, we can install these marsh feeders, which are essentially small miniature dams with holes in them that allow water to drain. It catches water during high tide, and then it allows water to drain at a controlled rate and inside the holes. And so then you can move this bar of how likely the habitat is to dry up and down. And by doing that, then you can get a range of differences between predation and desiccation. And because these things are usually large and contiguous areas of habitat, you can really add as many things as you like here. And so once you have a good idea of how each of these things influences the community and you get it controlled and you understand it, then you start to add in other aspects that we know are important for structuring any communities. So we know that the abiotic conditions are important in terms of filtering, and we know that species interactions like predation or competition are important. And then, but there are also other things that also filter any community, sorry. So here we removed some of the habitat heterogeneity by removing some marsh plants, and we can see the relative importance of habitat loss in the system. So to summarize, is even though these communities are right next to each other and are basically continuous, we did see clear differences in the communities in terms of their position and how energy flows through the system, and greatly impacting the scale. And this is almost certainly driven by hydrology as the massive variable, influencing the how extreme the level of desiccation is, and how intense the radiation pressure is. And what we see is we see greater variation in a very practice-based spatialing, and we see greater variation here than we do in hydrologically isolated wetlands that vary in their environmental conditions. And we don't get the same distance effects that we see if we use the traditional gradient. And so to bring it back to the circle, their position in the landscape and their environmental conditions means I think that kind of freshwater might be uniquely placed to bridge the divide between these things. And so we can maybe start kind of some sort of resilience or synthesis in diversity and new structure. And so with that, I'd like to thank everyone for coming today. And I mean, very fortunate with the grants I got and the money. And a lot of people helped me being able to plan, and especially on the land the last time, which was thought. But in particular, it's kind of breaking because without him, we would have gotten to all the sites in the first place, and he was very beautifully out here, and he very rarely had a fine on his face, field day, which is rough. And if there's anything worse than picking live invertebrates out of crap, night. It's picking dead invertebrates out of crap in the lab because you can't get all the samples. And so Aaron spent a lot of time sifting through the trying to find the invertebrates, which I was like, thank Jess for really having everything waiting in life and the scientist and person all around. And I like Hamish, or whatever it is he's doing here, and for generally being a very supportive advisor and letting me run with a project which first sounded quite carefully. So with that, I have your time.
We have plenty of time for questions.
One of the main findings from the first part of the talk was that there is a large extent to go on enough and community structure and richness of the town. To me, it's like being a lot of fun, the cities that do want a flow and water environment and one of the water. I guess I was curious as to how you think that might have affected your community structure and diversity results, and if you had any plans to incorporate water and climate.
So I'm going to repeat the question. So the question was whether I thought that the differences between these habitats in terms of how much fluid you receive, so the inland habitats are definitely lentic habitats, and the tidal sites are connected to main river steps, you might consider them a living habitat. Certainly, I do have information on the sort of preferences of taxa that we find there in terms of whether they're and certainly at the low marsh that was right next to the main stem, I think there probably is a little bit going on. We saw a lot of things like next stem caddisflies, which are photic, and information on that dragonfly was that yeah, it definitely prefers flowing water. So yeah, I think that there probably is a strong interest in flow here, probably less so in the higher tidal sites because the tide comes in very slow. It's not like I don't know, the coast where the water flows in very quickly. It seems to be relatively slow, and they tend to be off on the side. So I think the relative importance of flow might increase above the tidal concept. But certainly the previous studies tend to focus on the river stem as a whole, and they tend to look at the subtidal habitats. They basically driven a boat up an estuary, taking grabs from the bottom. And I think that's probably a very different environment than in tidal areas, especially considering that the direction of flow in these actually probably changes. Not only is the water changing relative direction.
Is anybody think that the same type of slowly due to tidal differences in marine systems, but not looking at the marine components
So in the question was whether the role of tidal hydrology in brackish or saline intertidal wetlands is important for influencing the flow structure. Yes, there has been some work, and I'm surprised there hasn't been more work considering the overall study of how sea level rise is going to impact tidal wetlands. Some people have found that, and this is probably very important for my work as well, that in addition to fish predators coming in with the incoming tide, that low tides, there seems to be a pulse of opportunistic terrestrial predators, like things like that, things that are coming down and basically snatching up the aquatic invertebrates that are stuck. And some work has found that increasing the hydroperiod, so stimulating sea level rise, has a deleterious effect on these communities. And so I don't know what would happen in terms of the fish, but I think that certainly the terrestrial aquatic community between the terrestrial and the marine environment is definitely affected by this increased period of flooding because then the time to spend can deal with these inverters for I think it's probably quite likely. So while in the aquatic realm here, the stress is desiccation. So when the water's not there, so I think there were a group of sort of semi-aquatic that like the fireflies or some of the other beetles that are definitely sort of little fringe classes that experience flooding as a stressor. And so there's hints at it with some actually found with MP7. This is semi-aquatic rather than fully aquatic. But certainly I had an idea of installing pitfall traps out in the marsh that have some sort of stop off, like when the water comes in, it closes it off to see how much these communities are being predated upon by the terrestrial. I suspect that there is a gradient predation, so down the tidal height gradient to get the relative because they have to get back up when the tide comes in or both the scale times.
Is there any role of seasonality or is it just hydrology all the time?
Yeah.
Like throughout the year, is it change how you
I think yes. Certainly, there are seasonal changes in the hydrology as well. So during the spring freshet, these areas, the relative changes in the tidal height are much greater because there's more water to get dammed up, and so it backs all these areas up. I think ice scar is probably really important for these changes to really soft fall often. So in the winter, there's probably fairly strong disturbance in that volume. Limits the number of fauna that can stay there throughout the entire year, letting the overwinter there. We did also see there are also strong changes in the technology of Marsh. Certainly looking at it there in May, the wild rice was just under ankles, and the opposite was over heads. While we did see some signal of seasonality, it really explained our variation.
The transects that you had in the high medium low, is there a no sensing buffer between the group? Did you run your transects perpendicular to the shore, parallel to the shore?
The individual transects or the points on the transect?
Oh, either. I'm just wondering, I think you had this really remarkable differentiation between high, medium, and low. That's even likely if you're sampling close to each other.
So the relative length of transects is different between both sides of the so in I mean these things are not scale, but the directionality of the transects. So this transect here, for instance, was This is only 100 meters long, and that is to account for the degree difference in slope. And so
You just divided the transect into 3 segments?
no, so we went down there at low tide, kind of where the lowest tide was, and then we chose the lowest point as our low point, and I guess we did that. Yes, we saw where the high water line was, so that is a high point, and then chose and so we because the transects were different lengths, the area between the two sampling points was different, but the slope, the amount of time to animated. So yeah, the length of transects remains between 8 and 8 meters.
Yeah, it's just remarkable, you got that differentiation. One from the transect.
Yeah.
Thank you.
I was surprised too.
And one quick follow-up, did I hear you say at one point that the vegetation is remarkably similar along the entire transect?
Yes.
Vegetation type changes dramatically, you went out and opened McLachlan or anything like that?
So we tended to avoid areas that were completely unvegetated, and we did draw out some quadrats to get some idea of complexity. And while there was strong differences between sampling and height of vegetation density, between the zones it was relatively homogeneous. Yes, it was mostly wild rice and bulrush and some. Yeah, the actual habitat complexity was relatively homogeneous.
Yeah. It's remarkable. That, of course, would be a possible explanation.
Of course,
That weren't.
Thank you very much, everybody, and
Sorry,